Hi, so I'm going to take you through question 3C because that's one that nearly everybody had trouble with, particularly part 2. And I'll also do the half equivalence question as well, just in case it comes in your exams, then you'll know. Okay, so first of all, question 3C. What we've got here is we've got a buffer, and as usual in a buffer we have undissociated weak acid and the salt of that acid, the important bit of which is the anion of the salt, the ethanoate ion. So just for completeness, let's put the two molecules up here. Ethanoic acid, as you'll remember, CH3COOH. That's our ethanoic acid, and our ethanoate ion is just that minus the hydrogen. So there we are, because that's reacted and made water. Good, so they're the important ions, and we're told the concentrations of each one, and we're going to use that in a minute. But let's do 3C part 1 first, calculate the pH of this buffer. And I suppose the only tricky bit is to remember that we're going to use the expression for Ka in order to find the pH of this buffer. Okay, so you're going to write your expression for Ka down, and that's our concentration of hydrogen ions times the concentration of our ethanoate ions divided by our acid concentration. Okay, so I think that's the intuition that you need to answer 3C part 1, and after you've made that intuition, the rest is just mechanics. So we would rearrange this for the hydrogen ion concentration, because we know we need that in order to get the pH. So when we rearrange that, we get this expression, which is the Ka times our acid concentration divided by our ethanoate ion concentration. Okay, so let's just see, earlier in the question you were given Ka earlier in question 3, and also your ethanoic acid concentration here has been given, that's 0.15, so that's this number here, so we're given that, and our ethanoate ion concentration, we're going to assume that's fully dissociated, of course, so that is here. So we're given all three of those in the question, so that would mean that we could substitute in those values, and that would give you a hydrogen ion concentration of 2.61 times 10 to the minus 5 moles per dm cubed, and then it's a straightforward use of that hydrogen ion concentration to get the pH of 4.58. Good, so hopefully that's clear. I think the difficulty, if anybody had a difficulty with C part 1, is just remembering that we started off with the expression for Ka. Okay, so that's 3C part 1. Let's move on to 3C part 2. So let's just have a quick look at our buffer, and we have 1000 cm cubed, which is of course 1 decimeter cubed of the buffer, which means that we have 0.15 moles of our ethanoic acid, and that means that we have 0.1 moles of our ethanoate ions in our decimeter cubed of buffer. So that's our buffer, and what we're doing is we're taking some hydrochloric acid Yeah, so we're adding hydrochloric acid to that buffer, and what the question wants us to do is it wants to find the number of moles of sodium ethanoate after the addition of that acid, and also the number of moles of ethanoic acid after the addition of those hydrogen ions. And then we're going to go on and find the pH. Okay, so we've got the starting concentrations. That's what we've worked out already, and so I think the intuition that you need is that when you're adding those hydrogen ions from the hydrochloric acid, they are going to react with the conjugate base, i.e. the ethanoate ions, and that's in high concentration, of course, as is usual with a buffer. And they're going to make more of the ethanoic acid. All right, so I'm just going to repeat that for you. I think the intuition you need is that when you add the hydrogen ions, those hydrogen ions react with the ethanoate ions and make more ethanoic acid. Okay, so with that in mind, that's the intuition. With that in mind, we're going to work through the numbers now. So the first thing to think about is the acid that we're adding. So this is the hydrochloric acid. So if we first consider the hydrochloric acid first, right? So the moles that we're adding, right? Moles equals concentration times volume. Concentration is given in the question is 1. And the volume is 10 cm cubed, but of course we deal with dm cubed in this equation. So our concentration is 1 mole per dm cubed, and our volume is 10 cm cubed, but in decimeters cubed you have to divide that by 1,000. All right, so the moles that we're adding of hydrogen ions from the hydrochloric acid is 0.01. Okay, and they are going to react with the ethanoate ions. Okay, so let's go on. So as we found out already, the moles of ethanoic acid before the addition of the hydrochloric acid is 0.15. Straight from the question. Okay, and the moles of ethanoic acid after the addition, all right, is going to be the 0.15 we started with, but we've created some more with this reaction, and we've created another 0.01 moles of ethanoic acid. So we get 0.16 moles of ethanoic acid after adding those hydrogen ions from the hydrochloric acid. Okay, so now we're going to switch to the sodium ethanoate, and so the moles of ethanoate before the addition, we already worked out in the at the very start, was 0.1 from this 0.1 here, and the moles of ethanoate after, okay, is going to be 0.1 because a bit of them has reacted with those hydrogen ions, all right, and so we have to subtract that 0.01 moles of hydrogen ions from our ethanoate ions, so we end up with 0.09. Now we can go back to our expression for Ka. But first let me just make some space. Use this space here rather than move on to another slide. Okay, so we're going to go back to our expression for Ka, and remember we rearranged that to give ourselves our expression for our hydrogen ion concentration, and that was Ka times concentration of CH3 COOH over our ethanoate ion concentration. And then we substitute in our values. Ka from the question, 1.74 times 10 to the minus 5, times our new ethanoic acid concentration, which is 0.16 divided by the volume, okay, because 0.16 was moles, wasn't it? Okay, so concentration is moles over volume, all right, but we're going to leave volume as V for a minute. All right, we have to divide that by our ethanoate ion concentration, and we've just worked that out as 0.09, but that was moles of ethanoate ions, wasn't it? So the concentration of ethanoate ions would be 0.09 over volume. And as it happens, those two volumes cancel, and so we just plug those numbers into our calculator and we get a hydrogen ion concentration of 3.09 times 10 to the minus 5 moles per dm cubed, and then that's a straightforward use of hydrogen ion concentration to come up with your pH, and if you do so, the pH comes out at 4.51. Which is what we were asked for in the question, hence find the pH of this new solution. And so we have we've done that. So this was part of the answer, this was part of the answer, and this was part of the answer to C part 2. There, so just at the risk of repeating myself too many times, I think the intuition that that we needed to make right at the start of answering C part 2 is that when you're adding those hydrogen ions from the hydrochloric acid, they're going to react with the ethanoate ions, hence use some of those ethanoate ions up, and the exact amount that being used up, i.e. 0.01 as we worked out, they are going to make more ethanoic acid ions. And that's the key intuition for C part 2. The rest is just plugging numbers into our familiar equations. Hopefully that's helped. I think what we'll do now is have a look at half equivalence. So this is question 4, A, part 3 and 4. They're the two parts, I think 6 marks, that were down to half equivalence or half neutralization. So let's just get our heads around what the question's asking us for. So it's given us a titration curve, and so as you'll be familiar with, equivalence point is here, and so that's neutralization. And so if you were to read down from there, you get about 11.8 cm cubed of sodium hydroxide added for the neutralization. Okay, so let's start with the balanced equation. Okay, so we're starting with an acid. I don't think we're told what acid it is. No, we're not told. We're just told a generic acid, H. So we'll call that HA. But we do know that we're adding the alkali sodium hydroxide to it. So let's write sodium hydroxide like that, and they are reacting. So you're going to get your sodium ions reacting with your. Let's just put our ion charges in there. So that's the salt that we're making, A minus. And of course, in any neutralization reaction, you're getting a water molecule being thrown off. Okay, so that's our balanced equation for the reaction that's going on. And so let's just get our heads around what's happening at neutralization. Okay, so at neutralization, all of the acid has reacted with the sodium hydroxide that you've added. Yeah, all of the acid has reacted with the sodium hydroxide that you've added. Yeah? Okay, so that means that at neutralization, i.e. neutralization, that means that at neutralization, when you've added your 11.8 cm cubed of sodium hydroxide, then there's no acid left. It's all reacted with the sodium hydroxide. So we can say that the concentration of HA is 0. Okay. So what you can then see, and I'll underline this in red, is that what we're not talking about neutralization. Okay. What we're talking about is when our concentration of HA is not 0, it's actually equivalent to the concentration of A minus. Okay. So we're talking about the concentration of this being equivalent to the concentration of this. All right. And so I think you can see that that is halfway through the reaction. Okay. So for those two concentrations, concentration of your acid, HA, to be equal to your concentration of your conjugate base, A minus, then you have added exactly half of the amount that you need to add to fully neutralize it. Okay, so that's when you see this expression here, all right, then you know that this is half neutralization. Half neutralization, or you could call it half equivalence, because this is the equivalence point. Equivalence, neutralization, same concept. Okay, so we've made that intuition. So that means that you can work out the volume of sodium hydroxide added now, which is your 11.8, which was your full neutralization, and you just divide that by 2 and you get your what was that, 6.5, 6.9 cm cubed of your sodium hydroxide added. Okay, and so then you look at your 6.9 and you just read it off the graph very roughly. I'm doing this, and I seem to remember the mark scheme said the pH was 4.3, and that's what you do. So first step is you recognize that this is this expression here is your half equivalence point. You know what equivalence is, 11.8. That's the vertical bit of your titration curve. So you just take half of your neutralization volume, 6.9, and you read from the graph what the pH was when you had added that number. Okay. So you might say, well, what's the point of all that? And well, the point of that is that half equivalence point is useful for working out the Ka of a weak acid, and that is the second part of the question, i.e. part 4 of this question. So let's go through that. So part 4 of the question wants us to determine the value for Ka. So let's write out our Ka expression. We've got Ka times the hydrogen ion concentration. Sorry, is the hydrogen ion concentration times our conjugate base concentration all over our acid concentration. Now, of course, at half equivalence, we know now that our acid concentration is equal to our conjugate base concentration. So that means that these cancel. Yeah, if one is the same as the other, they cancel, and therefore Ka is the same as the hydrogen ion concentration at half neutralization or half equivalence. Okay, so that means That means that if we knew our hydrogen ion concentration, then we'd be able to work out our Ka, which is what the question's asking us for. So how are we going to work out our hydrogen ion concentration? Well, in the first part, we've worked out what our pH is at this particular point. And so if we know the pH, we can find the hydrogen ion concentration. Let's just go through the process. So our hydrogen ion concentration, you'll remember, is 10 to the minus pH, which is 10 to the minus 4.3, which is whatever it is. And if that's what it is, then that is what Ka is. And I think that comes out at 5 times 10 to the minus 5, which is the answer to part 4, which you get 4 marks for. Okay, so that's half neutralization. I know we didn't find it in the spec, but that I did check that exam question, and that exam question was set under the remit of the spec that we're working to. And so if it was given to those students of that year, then it's possible that it could be given to you as well. So at least we've done it now anyway.